Let's look at section 2.2b, and today we're going to pick up some more derivative rules of sine and cosine, e to the x, a little bit more practice on writing these equations of tangent lines. So can you use the basic differentiation rules? Do you know your power rule, right? So the power rule is the one that says y prime of x raised to an n is we bring the n down front and subtract 1 from it. And you've learned that if I have, especially through delta math, if I have 1 over x to the 5th, then I'm best off rewriting this as x to the negative 5th to get my derivative as negative 5x to the negative 5 minus 1, which would be negative 5x to the negative 6. And then most of the time you have to write these as a positive exponent. So a little bit of practice on that. That was our power rule. And let's pick up some new rules today. Differentiating sine and cosine. The derivatives of sine and cosine are actually quite easy. So derivative of sine gives us cosine. And the derivative of cosine gives us almost sine, negative sine. So I want to do just a little proof of that for you. So here we go. All right, so let's just start out. We want to find the derivative of sine. I'm going to write it this way. I was going to do it the other way, but let's go this way. The derivative of sine. If I use the formal definition of derivative, it would look like the limit as h goes to 0 of sine of x plus h, right, minus the sine of x all over h. And then we're going to take and modify this a little bit using little trig identities, or the trig of the sum of two angles. We can split this into sine A cosine B plus cosine A sine B. So I'm going to take this right here and rewrite it into sine of x cosine of h plus cosine of h, cosine of x, there we go, and sine of h. And then I've got this minus sine x still there, all divided by h. And you're probably like, well, that doesn't help me a lot. I'm just going to rearrange things, a little addition, subtraction, rearrangement. I'm going to leave the sine x cosine h in the beginning, and in this minus sign I'm going to bring up close to my first term, and then I'll have plus cosine x sine of h at the end. No harm done, right? We can do commutative property on addition, limit as h goes to 0. Now I notice I have a sign in both of these, so I'm going to factor out that sign, GCF that, and that will leave me cosine h minus 1 plus cosine x sine h divided by h. Okay, so how is this helpful? You're like, yeah, we're doing a lot of fun stuff here, but how is it helpful? Well, take a different look at this cosine h minus 1 over h, and if h is going to 0, then it just so happens that this becomes 0. That was one of those special trig limits that we learned in chapter 1. Now I've got to complete my work here, and I've got cosine h, or cosine x, sine of h over h. Now you'll notice I'm writing this a little bit different. I divided this into two fractions. So they have the same denominator, so I split them up into two fractions. It was convenient to do so. And then I made this multiplying times sine x, and I just wrote h over this, which is fine because this is sine over 1, and 1 times h still gives me common denominator of h. So I haven't really broken any rules at all. And over here now, I'm going to slide that just a bit. And instead of one big limit, I'm going to chunk it into 2 little limits here. Sine h over h as h goes to 0 goes to 1. So we had a lot happen here. First off, you'll notice that this whole first term then, if I have 0 here and here, 0 times anything is going to give me 0. So I get 0 plus, and the limit as h goes to 0 of cosine x, essentially times 1, from here, becomes, well, the cosine of 0, and the cosine of 0, oh, not cosine of 0, let's just call it cosine of x, and leave it as a general derivative. What I came up with then is the derivative of sine x is cosine x. And that's pretty cool. That's one way of proving it. So if you don't want to memorize derivatives, I guess you could do the formal definition of limit each time and get it. All right, up on the top, well, you have it right above, but it's always good to practice. The derivative of sine x is cosine, and the derivative of cosine x is negative sine x. So derivative here, y prime equals 2, derivative of sine is cosine x. Done. I like to look at this a little bit differently. Rather than sine x over 2, I like to call it y equals 1/2 sine. Now I'm ready to take my derivative, and my derivative is 1/2. The derivative of sine becomes cosine x. Done. C has a couple terms in it. We're going to individually take the derivative of each. The derivative of x, if you remember from section 2.2a, what we did last time, is 1. And the derivative of cosine is negative sine. And there is its derivative. Taking the derivative of the natural exponential function, e to the x, will give us e to the x. That's kind of weird, isn't it? Yeah, the derivative of e to the x is e to the x. So I get, on this one, y prime equals 5 e to the x. B, y prime equals, well, the derivative of e to the x is e to the x minus 4, because the derivative of x is 1, isn't it? So I get 1 times 4. And C, I get y prime equals 7 times the derivative of e to the x, but it's itself is e to the x. The derivative of cosine is negative sine x. Now notice how I put this in parentheses, because we have an extra negative already placed into our function. This becomes plus sine x, correct? Be very careful when you get into these negatives. So that, just take it slow, right? Don't try to do everything so fast. Writing equations of tangent lines. So we are going to take the derivative so we can get the slope. They actually gave us the point, so that's sweet. We don't have to go find our own y value. But we do need to find our slope. And our slope is going to be coming from the derivative, correct? In calculus, we can take a derivative at a point. So I'm going to go f prime of x equals derivative of x is 1, and the derivative of this one is 4x, a little power rule. Now, I want to indicate I'm taking the derivative of the x value, which is 1. Oops, got an issue going on here. All right, so if I want to take the derivative at 1, I plug it in to my derivative, my general derivative. And I get 1 minus 4 gives me negative 3. So the derivative at 1 is negative 3, and we go into writing the equation of our tangent line. Y minus y1 equals the slope x minus x1. If you like to have I'm going to put x sub 1 there. X minus x sub 1. That's what I just filled in, didn't I? I used the point slope form and put in everything that we needed to know. Awesome. For B, write the equation of the tangent line at the given value of x. All right, so they gave us x equals 1, but I need to make a y value for that. So I'm asking myself, what is the y value? So we will substitute 1 in for our f of x, and that will look like 1 there. Looks like we're coming out with 2, doesn't it? So when I plug in 1, I get out 2. Ordered pair, 1, 2. Next, let's go after our slope. So the slope, which is coming from the derivative, make these connections, write them down. It helps your brain a ton. We need the derivative, don't we? So I need f prime of x equals, I need to take the derivative of this. So I'm going to rewrite my function into rational exponent form. Now, power rule says 2 times 1/2 x to the 1/2, whoops, why did I write negative? 1/2 minus 1 makes this x to the negative 1/2, which could be written as 1 over square root x. There's our general derivative. Now, let's evaluate that general derivative at x equals 1. So I put 1 over square root 1, and 1 over 1 is 1. We have a slope of 1. Back to writing the equation of the tangent line. Can you do this by yourself? I'm sure you probably can. Y minus y1 equals the slope evaluated at x sub 1, x minus x sub 1. Plug and play. Y minus, my y value was 2, equals the slope, which is 1, x minus x sub 1, which was 1. There's the equation of the line that is tangent to our graph at the point 1, 2. We've done one like this one before. It says find locations of horizontal tangent lines. At what point or points does the graph y equal x squared have a horizontal tangent line? Well, you know what? Get a little visual in your head, guys. This has got to be a parabola opening upwards. In my head, I'm thinking there's one location where I have a horizontal tangent line. Horizontal tangent lines, just for knowledge's sake. What is it asking us to find? Well, horizontal tangent lines have a slope equal to 0. So in my head now, using calculus, that means there is some location where my derivative equals 0. Just a little brain work there. Mentally think this through before you start. All right, then I need to get a derivative. Y prime equals 2x plus 4. I want to know where y prime equals 0. So I'm going to write that because it's just conveying knowledge. And conveying knowledge is a really good thing when you have somebody grading your work. So let's subtract 4, and we get negative 4 equals 2x. Therefore, x is negative 2. It occurs when x is at negative 2. If you want, go graph that parabola and see if it works out. I guess that is ensuring tangent line to a given point. I'm not sure if you guys have number 10. Oh well, that is enough, and we can go from there. So have a good day. You know what? I see that I have it in my notes. and I think it probably would be a good one to cover. So you have it in your notes too. I'm just going to make a clean screen, and let's do example 10 as shown in your notes. I'm not sure where my screen is from this. So they give us a function, and notice that extra k, and then they give us another line, 6x minus 2, and it says find the value of k so that the line is tangent, so that that line is tangent to our function, and our function is the cubic function. All right, so, wow. What can I do? If that line y equals 6x minus 2 is my tangent line, then from the tangent idea, I can figure out the slope. The tangent line has a slope of what? Well, looking at this line, I see a 6, and it is in slope-intercept form. It has a slope of 6. Okay, how can I get information about slope from my original equation? I can take the derivative, and then I want to set my derivative equal to this slope of 6. And then that should tell me the x value that yields the 6. So let's first step, let's get a derivative. Let's find the derivative of f of x. So f prime of x equals, shouldn't be too bad, 3x squared plus what? Here's where it's a little tricky. K is just a number, and the derivative of x to the first is simply 1, isn't it? So I essentially get 3x squared plus k. F prime of x equals 3x squared plus k. Now, I want second step. I'm already thinking through it, but let's write second step. We want the tangent line, or the tangent line slope to equal 6, because they told us it has the tangent line, right? So I'm going to go f prime of x must be 6. Or 6 would equal, and maybe I'll do it this way, 3x squared plus k must equal 6. And what can I do with that? Well, I could solve for k. K equals 6 minus 3x squared. And then I can substitute this back into my original equation. Okay, so my third step, kind of thinking this through, if the original equation has a tangent line, then they have to hit at the same x. X from here must equal an x from there, correct? So I'm going to take x cubed plus kx and set it equal to 6x minus 2, which was that tangent line they talked about. And instead of k, I'm going to substitute the 6 minus 3x squared, because now I can get an equation that is solely in x's. So let's just see what we've got here. We have got x cubed. Ooh, I lost my x here. Plus 6x minus 3x cubed equals 6x minus 2. Keep accumulating like stuff. So I'd have negative 2x cubed plus 6x equals 6x minus 2. Subtract a 6x from both sides, and then we can divide by a negative 2. X cubed equals 1. X equals 1. But that's not what they ask us for. They ask us to find the k value. So my fourth step is going to be finding k, and I have an equation that talks about k. K equals 6 minus 3x squared. So substituting the known value of 1 for x, we would get k comes in at 3. That is a very involved problem, but doable. It just takes a little bit of thinking. I think the key piece in this is to think about if I have an original curve, it was cubic, and a tangent line, they have a point in common. And because they have a point in common, that means that the xy value is shared. So we can think about the x sub 1 being equal to the x sub 1 at that location, and that allows us to say these x's must equal these x's. Okay? Very good. Your homework is this worksheet, and I want you to skip problem 9 on your worksheet. Very good. Thank you.